In this video, we're going to briefly discuss Euler paths, a famous and common application of graph theory. So first we're going to ask the question, what is an Euler path? In simple terms, an Euler path is a path that goes through every edge of a graph exactly once. So edges cannot be traversed more than once. This doesn't apply for vertices, however, which may be visited multiple times. A slight variation on an Euler path is an Euler circuit, which is essentially an Euler path beginning and ending on the same vertex, as you can see in figure 1. So Euler's theorem is a theorem described by Euler to categorize these graphs and identify their suitability for Euler paths. If a graph has more than two vertices of odd degree, it will have 0 Euler paths. If a graph is connected and has 0 or exactly two vertices of odd degree, it will have at least one Euler path. And if a graph is connected and has 0 vertices of odd degree, it will have at least one Euler circuit. A degree of a vertex, in case you weren't aware, is the amount of edges connected, or the amount of links or lines, however you want to word it. The primary method for finding an Euler circuit in a graph meeting the criteria in Euler's theorem is by applying Fleury's algorithm, which states if there are two odd vertices, you start at one of these. If there are 0, you can start anywhere. The second part says you follow the edges one at a time, deleting the edge after you have passed through it, and you should always prioritize the non-bridge edges over the bridge edges to avoid disconnecting the graph. So a bridge edge is any edge that is connecting that is the sole link to one vertex. So if you got rid of this, then that vertex would no longer be connected. So you prioritize the non-bridge edges over the bridges to avoid disconnection.
So now we've covered the basics of Euler paths and circuits, we're going to have a go at finding some ourselves. So to do this, we're going to go through Euler's theorem and test all parts of his theorem using Fleury's algorithm. So the first part of Euler's theorem states that if a graph has more than two vertices of odd degree, it will have 0 Euler paths. Right, so let's test this ourselves. Let's draw ourselves a graph here. Drawing our vertices just to make it clear. The first thing you do when you get a graph like this is number the vertices with how many edges they're connected to, or their degree. So we got 1, 3, 2, 3, another 3, another 3, one more 3, and a 2. So now how many of these vertices are of odd degree? Well, we've got 1, 2, 3, 4, 5, 6. Quite clearly, 6 is more than the 2 odd vertices needed. So, according to Euler's theorem, this will have 0 Euler paths, and we can see this by simply testing this by trial and error. So, if you start anywhere, you would always end up going back on yourself in attempts to cover all vertices. No matter where you started, there will always be you would always have to go back on yourself through an edge that's already been visited. So in this case, Euler's theorem, you can see by eye, is correct and applies here, as you can see. Now the second part of Euler's theorem states that if a graph is connected and has 0 or exactly 2 vertices, well, odd vertices, sorry, I should say, it will have at least one Euler path. So this is our theorem, which we're going to test. So we're going to make ourselves a graph here. So, yet again, we're going to just mark out our vertices, and then we're going to label them with the number of edges they're connected to. So we have 2, 4, 3, 3 and 2. Looking back at the part of Euler's theorem, it says if the graph is connected, which it is, as you can see, you can reach any point from any other point on the graph. If it's got 0 or 2 odd vertices, here we go, we have 1, 2 odd vertices, all these are even, it will have one path. So we've had it confirmed now by Euler's theorem that this graph will have at least one path. Okay, so now it's been confirmed by Euler's theorem that this graph will have at least one path. We can use Fleury's algorithm to find this path. So Fleury's algorithm states, if you remember, if there are 2 odd vertices, start at one of these. If there are 0, you can start anywhere. So in this case, we have 2 odd vertices. Let's start at 1. Let's start here. I'm going to redraw this graph just in a way that will make it a bit easier to visualize the process. I'm going to connect them with dotted lines. I'll explain why in just a second. So I've drawn this graph with dotted lines. I'm going to number our vertices again just to remind ourselves. 2, 3, 3. So I've drawn these with dotted lines because if you remember, in Fleury's algorithm, the second part says you follow the edges one at a time, deleting the edge after you've passed through it. So in this case, when I fill in the dotted line, it will mean effectively that this edge has been deleted. So we'll start at this vertex here, and we're going to follow the edges one at a time, and after we've gone over an edge, we're going to delete it so we know not to pass over it again. Fleury's algorithm also says you can always prioritise the non-bridge edges over bridges, so what that essentially means is try to not disconnect the graph if possible. Sometimes the very last edge will disconnect the graph, but always prioritise the non-bridge edges. So we'll start here. We can go anywhere really from here. We're going to go over here to our vertex with degree 2. That path is now deleted. I'll just draw an arrow to show our direction. And then we can go up here. That path is now deleted. And then we can go, well, we can go in any sort of direction here, but let's go back down here just to show. We're back at our vertex. Our starting vertex, that's absolutely fine. You're allowed to cover vertices more than once. It's just the edges which are not allowed to pass over again. So we'll connect these 2 odd vertices now. And then again, we can go up here, we can go here. Let's go here. And then the rest fills itself out for you, really. So we've started here and finished here. Because we've started and finished at different vertices, this is an Euler path, not a circuit. But here we can confirm that Euler's theorem is yet again correct, thanks to Fleury's algorithm being possible. Finally, we're going to test the last bit of Euler's theorem, which states that if a graph is connected and has 0 odd vertices, it will have at least one Euler circuit. So this time we're looking for a circuit rather than a path. So a reminder of what an Euler circuit is, it's essentially an Euler path which starts and finishes on the same vertex. So again, we're going to draw a little graph to try and visualize this. Bear with me. Drawing is pretty poor. So now we're going to go number of our vertices as usual. So 2, 4 lines there, 2 here, 4 here, 2 and 4. And this confirms to us that there is an Euler's circuit present. So now it's time to apply Fleury's algorithm yet again. I'm going to draw out the graph in the same way I drew the last one, connecting the vertices by dotted lines rather than straight lines, just to make the visualization a little bit easier. It works well for me, this. And we're going to just label the vertices again in the same way as last time. So now we've labelled our vertices, we can apply Fleury's algorithm. So the first part states if there are 2 odd vertices, start at one of these. If there is 0, we can start anywhere. Obviously, in this case, we have a full graph of even vertices. We can start anywhere we like, and you'll be able to make an Euler circuit from any of the points, supposedly, according to Euler's theorem. So in this case, we're going to start here, and we're going to see where we finish. So we can go anywhere we like from the start. We're going to just cut across here. There's our first part. Then we're going to come down here for our second part, and we can complete the triangle back to the start. And if you see here, when we've completed that inner triangle, the rest of it, you can sort of, works itself out for you, really. You should be able to visualize the rest of the graph now where we're going to go, but I'll draw it in anyway. It's nice and straightforward, this one. Once you've cut out the inner triangle. I haven't drawn that very well, have I? Here we are, we've started and we finished on the same vertex, which means that this graph does indeed have an Euler circuit, and Euler's theorem can yet again be confirmed.
So now you're probably wondering, why are Euler paths relevant and what are they used for? Well, they have lots of practical everyday uses. For example, postmen, a woman, painters and pilots will all be using the fundamentals of graph theory and Euler paths, whether they realise it or not. Because obviously a lot of the postmen and women and delivery drivers nowadays will have an app on their phone that uses it, that does it for them, but these all use the fundamentals of Euler paths and applying Fleury's algorithm. Arguably the most important use, and this is a problem that began the concept of graph theory, is the Königsberg bridge problem. So in the 1700s, Euler was asked to look at this problem by the people of Kaliningrad in Russia. Essentially, he was asked to find a way that someone could walk over all 7 bridges exactly once, as you can see in the figure on the right. And this sparked his investigation into the branch of mathematics we now know as graph theory.
So the map of the Königsberg bridge problem, which you've just seen in the slides, can be rewritten as a graph, just like so. So each of these vertices is representing the different parts of land. So this we're going to call A. This is the island. This is the northern bit of land. This is the southern bit of land. And this is the land that you can see in the east. We're going to connect them by bridges. So from A to C, there are 2 bridges. From A to B, there's only 1. From C to B, there's only 1. From B to D, there's also 1. And then there's 2 again between A and D. So this is how you can visualize the Königsberg bridge problem as a graph, which is what Euler was trying to do. Now, if we look at this graph and apply what we now know as Euler's theorem, we can work out whether it is possible to complete the Königsberg bridge problem. The first thing we do is number the vertices with how many edges, their degrees. So we have 5, 3, 3, and 3. And if you remember, in Euler's theorem, if there are more than 2 odd vertices, it is impossible to draw an Euler's graph or circuit. In this case, there are 1, 2, 3, 4 odd vertices. All vertices are odd. Therefore, it was deemed that this problem is impossible.